Hello, in this lecture, we are going to take the topic called as the postulates of quantum mechanics. In the previous lecture, I have discussed the approach that we are going to take in learning quantum mechanics, and I've stated that the approach in quantum mechanics initially that I would take, and in general, most of the textbooks that they take is the postulatory approach. Okay, and see, as I already stated, that quantum mechanics is based on certain postulates, and all of these postulates derive their inspiration from the experimental findings. Okay, and all these things have been discussed in different lectures, which are there in the playlist. But for now, I would just focus on developing these postulates or writing these postulates, explaining you all of these postulates uh, with 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 all patience. Okay, so I would just request you all to keep great focus on this particular lecture, because once you have, I would not say a very depth of understanding in this topic, but at least if you are comfortable with all of these postulates, then you can at first start working with different potential problems. And once you start working with different potential problems, uh, there would come a stage in learning quantum mechanics that you will be able to understand all of these things uh, in retrospective. For that, you would need a certain background of linear algebra that I'm going to teach in mathematical physics side by side along with these lectures. So don't worry about the progress. Just concentrate and understand. If you cannot understand them in very depth, just make sure that you just follow all these kind of postulates that I'm going to mention. Okay. So without wasting your time, I'm going to start. Okay. So postulates of quantum mechanics. As stated in the previous lecture, the prime question of quantum mechanics or the physical problem that are governed by quantum mechanics is, I'm just going to revise it for you. Uh, the first problem that one needs to understand or one needs to address is how a quantum state be described at a certain time, and one would understand uh, that this is not very certain. One would understand that probability would govern it. Okay, so we'll come to all those things. So how quantum state can be described at a certain time? Uh, how does this evolve? This quantum state evolve? How does this quantum state evolve? And how to calculate various, or you can say how to assess various physical quantities, like we study in classical mechanics. So the same physical quantities here, how, what are the analogous forms, or how do we understand, or what is our understanding of the physical quantities like energy, uh, like momentum? Okay, in in quantum mechanics, analogous, whether the treatment is analogous or there's some different kind of treatment. Okay, so basically, in order to address all these questions, we need to resort to something called as postulates of quantum mechanics. Postulates of quantum mechanics. So address these uh, questions. One need to understand. One needs. One goes uh, in what you will take something called as postulates of quantum mechanics. postulates of quantum mechanics. So the first postulate is again kind of okay. One thing that I need to mention that again, as I told you, I would just assume that you may have gone through basic quantum mechanics, okay, till the undergraduate level. This is a first prerequisite for these lectures. Side by side, if you can just make yourself comfortable with linear algebra with my lectures, that would be very good. If that happens to be the case, then you will be able to understand this theory very well. But for now, if you are listening to this particular lecture, I would just insist, just understand whatever I'm saying. Just keep them in your mind right now, okay? Just don't think much about this, that why it is happening and why it is being written. Just understand that these are all postulates, okay? When I'm saying postulate, as I've mentioned, these stem from the experimental observations or experimental findings. So you have to trust them, okay? You have to trust them. So I'm starting it, okay? The first of the postulate, okay, the first postulate dictates the state of the system, okay? Dictates the state of the system. So how do we represent the state of the system here, okay? So as we know, the first thing is state of the system. Okay. So it is postulated in quantum mechanics. So in quantum mechanics, it is postulated that every particle or you can say every quantum entity or entity which is governed by quantum mechanics, every particle is represented by a, an abstract uh, concept called as wave function. And I would insist that you just see the lectures on the wave particle duality that I will teach. Then you will be able to understand this kind of formalism. But right now, just keep in mind that whatever I'm writing, you just make peace with it. So in quantum mechanics, it is postulated that every particle is represented by an abstract concept called as wave function, which in general, although lately we'll see that we can also represent wave function in position, in momentum space, but right now, which is a function of space and time. So what does it require from us? It would require from us, first thing, that is spatial, that is a coordinate, and another thing would be a time. So this particular wave function encapsulates all the information. Encapsulates all the information about the system it represents. About the system it represents. Okay, this is the first thing. Okay. Okay. Now, before heading to this, I will just go through a few of the things. And so something called as Dirac notation, and I'll come to all these things. Just don't worry about it. Just understand in Dirac notation, I will write the same statement. That is the state of a physical system the state of the physical, or you can say quantum system is specified at any time t by a state vector. By a state vector represented in this fashion. Just don't worry, I'll come to all these things. By a state vector in a Hilbert space. What is this Hilbert space? Just don't worry, I'll come to this also. In a Hilbert space, I'll dissect all these things in brief, because as I told you, all of these things I'm going to delve much deeply in the set of lectures on linear algebra. Right now, I'm just going to give you some kind of introduction to whatever I have written. Okay. This particular construct that you're seeing right now, society, this particular society contains all the requisite information. So basically, this is a wave function which is represented, or which is denoted by this way. So it contains all the requisite information about the system. Okay, so now let us break it down, break it in a smaller way. The first thing that one needs to understand is what is a Hilbert space. Okay, and before understanding what is a Hilbert space, let us first briefly understand what is a vector space in general. Okay, so what is a vector space in general? So, and these are just brief things that I'm going to tell you. Again, as I mentioned, more detail will be shared in the lectures in the linear algebra. Okay, so first thing, let us understand what is the abstract concept of vector space in mathematics, and it is very quite important concept in general. So basically, this kind of mathematical machinery of the vector spaces is going to be employed in the study of quantum mechanics. Okay, so let us just understand what is this vector space. So let me just write. What are these vector spaces? What are these vector spaces? Okay. And I'm going to teach you this with an inspiration from R square. So just let me write what is a vector space. Okay. So vector space is an algebraic structure. The first thing that comes to mind is that this is an algebraic structure. The group is an abstract algebraic structure. The similar way, I'll say that this is an abstract algebraic structure. Okay. Basically, this contains two kind of elements. In simple way, I'm writing. Okay. One I would say vector, other would be scalar, and the scalar would be from some field. So just don't get into this thing like field. You can take right now that real number system forms a field, complex number system also forms a field. So one is called as vector, another is called as scalar, and these scalar entries come from field. Okay, so basically you will have some set of vectors, and then you will have some set of scalars. Okay, and there is a definition. There are two definitions. So there are two well-defined operations. So there would be two well-defined operations. I'm teaching all these things in very, you can say, a non-polished sense of teaching when it comes to vector space. Again, I'm insisting that more of these technicalities I'm going to discuss in linear algebra. Okay, two well-defined, you can say, well-defined operations, I would say. There are two well-defined operations. The first operation would be addition. Okay. Another would be scalar multiplication. So there would be vector addition, and there would be something plus scalar multiplication. Now you just keep in mind what is R square. We'll understand that R square over R forms a linear vector space. We'll understand it, don't worry. But just understand what is R square. So what is R square? What is R? So if I say that X belongs to R and Y belongs to R, then XY belongs to R square. So basically, what does R square represent? R square represent a plane. So what does R square represent? R square represent a plane. It represents a plane. Okay, it represents a plane, a Cartesian plane, exactly. Cartesian two-dimensional plane. Okay, now just keep in mind the properties that I'm going to write for vector space, and just try to develop in mind some analogy with R square. So that would be easy to understand. Okay, that would be an easy thing to understand. The first thing is that this, with respect to vector addition, with respect to vector addition, with respect to vector addition, I'm writing that abelian group is formed. Abelian group is formed. So basically, what are these? What I'm going to write now is the properties which must be applied so that we can define vector space. The first thing is that these elements, these are the vectors. If we are going to add, and if we are going to make an algebraic structure on the addition of these vectors, they are going to form an abelian group. And what do you mean by abelian group? The first thing that needs to be seen is closure. The first thing that needs to be seen is closure. That is, if I'm writing, let's say, there are two vectors. Let's say I'm signifying them in more physically appropriate way. That is psi and phi. Let's say psi and phi are two vectors. Okay, are two vectors. Or you can say elements. Why I'm saying elements? Because at times people get confused by thinking that they are only vectors in, so to speak, like they just fix their mind with this vector notation. I'm not saying vectors. Vectors can be here functions as well. So, like for example, if I say does the real continuous functions form a vector space? Yes. So basically here these are elements. Just don't always associate them with vectors. However, right now, initially I'm going to start with R square as an example, so that you just you can just get some know-how of what is R square. Okay. And how does R square form a linear vector space? So this is my sort of drawing parallels between the two so that you can understand. And as we are going to see, as we are going to approach different quantum mechanical problem, you're going to you'll just self-learn all these things. Don't worry about it. So what are the properties? The first property is these, the vector elements, that is psi and phi. If they're added, okay, they again become vector. So basically, so if psi and phi are two vectors of a space, okay, then psi and phi are also vectors. Okay, this is how we define something called as closures. For example, in the easier way, if I write, let's say, does addition form a closed operation with respect to real numbers? So does addition, if this is a binary operation, does it form a closed operation with respect to real number? Yes, indeed yes. Because if you take a real number x, if you take another real number, let's say y, and if you add them up, you again get a real entry only. So basically, Addition of two real number is again a real number. So you can say that addition with respect to addition, real numbers. So addition forms a closed operation with respect to real numbers. Okay, you can say set of real numbers are closed with respect to the binary operation sum. So basically here what I'm saying, the first operation that comes in the definition of the vector space is the vector addition. That is, if I've already told for vector space you need two kind of elements, that is a vector and another one is scalar. Scalar derives its entries from the field. One of the field can be R, that is real numbers form a field. Complex numbers also form a field, and you need to assert two well-defined operations. The one operation is called as a vector addition, the other operation is called as a scalar multiplication. So with regards to vectors, the vector addition forms an abelian group. So for first thing that needs to be checked in abelian group is that whether closure holds or not. So if psi and phi are two vectors, and these vectors I would write elements of a space, then psi plus phi are also vectors of the same space. Understand, of the same space. If this is the case, then it qualifies the property number one, that is a closure. The second property when it comes to abelian group, the second property is commuted, that is associativity. Associativity. Okay, sorry for the interruption. Okay, sorry for the interruption. Uh, okay, so the first thing that needs to be seen is that with the psi and phi, uh, these are the elements from the vectors. Are they closed with respect to addition or not? The second property is whether the operation is associative or not. Whether the operation is associative or not. That is, if I'm saying that there are three vectors psi, phi, and another vector is, let's say, chi, then psi plus phi plus chi should be equals to psi plus phi plus chi. The third property that one needs to see while checking whether with respect to addition, with respect to addition, vectors form an abelian group or not, The third property is the existence of a new existence of zero vector, you can say, or you can say uh, existence of identity in more mathematical appropriate way. Existence of identity, that is, does there exist some zero vector, let's say O, belongs to this belongs to some space where these elements are also there, that is psi, phi, and chi, such that phi plus zero vector is equal to zero vector plus psi is equal to psi. Okay. Okay. Now, okay, the, the fourth thing should be the existence of inverse element. That is, does there exist some inverse element for, let's say, psi? So, for example, if there is psi in some space, then minus psi should also be contained in this space. Okay. If there is psi contained in a space, then minus psi should also be contained in that space, such that psi plus minus of psi should give you back the identity element, which is the zero vector in this case. Okay. So if psi is there in some space, and in that particular space, if minus psi is also contained, such that psi plus minus psi gives you back the identity element, which is the zero vector I have written here, then all these if all these properties are there, that is, if with respect to addition, if vectors, if they add up to give us another vector in the same space, that is, if closure holds. Secondly, if associativity holds, if there is existence of zero vector, and if there is existence of inverse element, all these qualify the properties for claiming that the vectors form a group with respect to addition. Now, what about abelianness? So, if my vector addition is commutative, then we can say that with respect to addition, my vector forms an abelian. So, this is the first, you can say, chunk of property that needs to be seen while qualifying some algebraic structure and a linear vector space. So commutativity means what? That is psi plus phi should be equal to phi plus psi. Okay. So this is the first chunk of properties that needs to be seen. Second chunk of property deals with the multiplication. Okay. Deals with the multiplication. So as I told you, in defining vector space, you need two elements. That is, one is vector, not exactly the vector. Okay. I'm not saying they are not vectors. They can be vectors. Like, for example, R square over R forms a vector space. So here, you can associate elements in R square with vector. The vector, like the geometric one that we know. But vector here can even be functions. Okay, can even be functions. So just don't. This is just an abstract kind of formalism. So you are just going to get into all these kind of thing as you are going to progress. But right now, what I'm going to do is I'm going to formulate the same theory for R square, and then you will be able to understand what I mean. Okay. And just don't forget what we are studying. Right now, we are studying the postulate number 1, where I stated that in quantum mechanics, it is postulated that every particle or entity which is governed by quantum mechanics is represented by an abstract concept called as a wave function, which is a function of space and time. Although, when I'm going to progress, I would also say that wave function can be represented in momentum space. So just now I'm writing, which is a function of space and time. What is space? You require a coordinate, and you require another thing is called as time. And this wave function encapsulates all the information about the system it represents. Okay, these are all very abstractly written things. The only suggestion from me as a learner of quantum mechanics is that once you are going to deal with some physical problem, you're going to understand whatever I'm saying. Okay, in Dirac notation that we're going to study right now, in very brief, that the state of physical system, quantum mechanical system I'm speaking, is specified at any time t by a state vector psi t in a Hilbert space. Now, what is this Hilbert space? I'll come to this. very briefly only, because this is a portion of a mathematics branch which is called as a functional analysis. Okay, so this is very depth. We are going to just skim and we are just going to see something called as the squarely integrable functions. And psi t, and this psi t, that is a state vector, contains all the requisite information about the system it represents. Okay. Now, the first thing before understanding what is Hilbert space, I'm coming on to vector space. What is a vector space? Vector space is an algebraic structure where you require two kind of elements. You can say two kind of things. You can say one is vector, another is scalar. Scalar entries would come from the field. For simplicity, I will say right now I'll be more concerned with the real number system. Real number system forms a field. And okay, so what I'm going to do, I'm just going to write what is vector space, what is the definition of vector space, and then I'm going to draw a parallel with R square so that you can visualize what I want to say. So first thing is the vector elements with respect to addition forms an abelian group. What is an abelian group? You know from your BSc classes that abelian group qualifies all these properties that I've stated. Now comes what are the chunk of properties with respect to multiplication. So I'm writing scalar multiplication here. Now this is another operation. Okay. Okay. So with respect to scalar multiplication, the first property is, you know that if I multiply a scalar with respect to vector, I get again a vector. So let's say if psi and phi are, let's say, two vectors in space, are two vectors in space, then a psi would also be vector, b phi would also be vector. So a psi plus b psi is also vector. And what are these a's and b's? These a and b are scalars. Now, second, with respect to addition, there should be distributivity. So what do you mean by distributivity? That is a psi plus phi should be equals to a psi plus a phi. Third, there should be associativity when it comes to multiplication, scalar multiplication. That is a b psi. If I do it in this fashion, a b psi should be equals to what? It should be, if I write a b psi, I can write it in this fashion also, a times b psi also. So there should be associativity in the when it comes to multiplication by multiplication of vector with scalars. Okay, associativity. Also, there should be something called as identity element here. So there should be an identity element I, such that if I multiply this identity element with psi, or psi with identity element, it must give me back psi. It must give me back psi. So these are the properties when it comes to, you can say, when it comes to defining linear vector space. So basically, this, again, I'm reiterating, linear vector space is nothing but it is an abstract algebraic concept. This is the first thing that I want to mention. That is, linear vector space is nothing but it is an abstract algebraic concept. What is abstract algebraic concept? Here, in order to define what is a vector space, we need two things. First thing is vector, another thing is scalar. The first thing is vector, the another thing is scalar. With respect to vectors, or you can say vectors should form vectors should form an abelian group with respect to the addition operation, okay. And another thing is called as the scalar multiplication. So when it comes to scalar multiplication, the first thing is that the scalar multiplication should be closed. That is, if psi and phi are two vectors in the space, the a psi plus b psi is also vector. The other property is distributivity with respect to addition, associativity, existence of identity element should also be there. Okay. Okay. Have I written? Oh, sorry. Another property apart from all these things is called as the distributivity with respect to addition. Sorry. So another property is distributivity with respect to addition. I forgot to write the property distributivity with respect to addition. With respect to addition. So distributivity with respect to addition. That is just give me. Okay, that is, if I'm saying that there are two scalars, let's say a and b, if there are two scalars a and b, then a plus b times v, I should write psi, should give me a psi plus b psi. Okay, so if all of these are true, if all of these properties are true, that is with respect to scalar multiplication, we have these property, there is a distributivity over addition, then I would say that let's say all these elements, of vectors are coming from a set V. Let's say all these vectors are coming from a set V, and let's say this these scalars come from field R. Let's say R only. So then, if all these properties are true, then I say that V forms a vector space. We will say that V forms a vector space over R. If all these properties are true, then we say that V forms a linear vector space over R. Okay, over R. So this is first thing that one needs to understand. Now, I know this is quite rigorous for you. Let us understand an algebraic. Let us understand the space R square. The space R square over R. Now, when I'm saying over R means this is your scalar. That is, this is scalar which will take entries from a field, and this field is nothing but this is a real vector, real number system. Real number system is a field. And what is R square? So R square over R represents a Cartesian plane. It represents what? It represents Cartesian plane. It represents a Cartesian plane. Okay, now let us understand. So does R square over R? So understand, the scalar entries will come from the real number system, and R square would dictate the vectors. Okay, so does R square over R form a vector space? From a vector space. This is the question that I'm asking. Okay, so again, if one needs to see that does it form a vector space or not. Now let us understand geometrically what does it mean. Geometrically, it means that I'm talking about a Cartesian plane. I'm talking about a Cartesian plane. Okay. And I know that if I take two vectors, let's say this is my vector number 1, and this is, let's say, vector number 2 in the Cartesian plane. So let's say if vector v1 vector and v2 vector. So basically, one can understand that the arguments of these v1 and v2 are real numbers only, because this is simply xy plane I'm talking about. One should not confuse that I'm just taking first quadrant. I can take it in anywhere in the space. Okay. So if v1 vector belongs to r square and v2 vector also belongs to r square, then if I perform an addition operation, where does this lead to? So this will again become some other vector, let's say capital V vector, and this is also contained in R square. So the first property, that is a closure with respect to vector addition, is quite clear. So one can say that closure holds. The second property is quite easy to see from your standard 11, that the vector, if v1 vector, if I add to v2 plus v3, if I take the vector addition here, it is same as v1 vector plus v2 vector plus v3 vector. This is something that I'm leaving up to you to perform. We just take three vectors, and just perform it geometrically, and you will be able to satisfy yourself that associativity holds. Okay. Now, the other property, the third property, was the existence of the identity element. So existence of identity element with respect to the addition operation, you know that there is a null vector. So there is a null vector which belongs to R square. There's a null vector which belongs to R square, which where both of the coordinates are 0, 0, that is origin. So I'm defining this null vector as 0, 0. I know if I take any v vector, so let's say v vector I'm taking x, y. So if I know that if I add with v vector, that is x, y, if I add it to the null vector, that is the 0, 0, I'll again get back x, y. So basically, there is existence of this identity element. There's existence of this identity element, or I told you 0 vector with respect to the. So there is an existence of this identity element or 0 vector. With respect to what? With respect to the vector addition. 0 vector, sorry. Okay. Okay. Now, as we know that for if v vector belongs to, let's say v vector belongs to your two-dimensional space. Let's say I'm drawing 2 dimension in this way, so that you just don't get used to only first quadrant. So if v vector is there, certainly minus v vector is also there. Okay. So if v vector is there, then minus v vector is also contained in R square. So if v vector is contained in R square, then minus v vector is also contained in R square. And if I add this v vector with this minus of v vector, then I will get back the identity element, which is the null vector. I'll get back the identity element, which is the null vector. So basically, there is existence of inverse element also. And also, you know that whether I add v1 vector plus v2 vector, or if I do it the operation v2 vector plus v1 vector, it is one and the same thing. So I can say that commutativity also hold with respect to the addition. So with respect to the vector addition, commutativity holds. So I can say with respect to addition, vectors in R square form what? They form an abelian group. Now let us define let us see the definitions of the scalar multiplication. The first thing we know that scalar multiplication is well defined. So this is quite easy to see from our standard 11th classes, that a scalar multiplication is well defined. And what does it? What does one understand from scalar multiplication? Let's say if there is a vector v, and if I multiply it with lambda, so let's say if lambda is greater than 1, this vector will enhance. If lambda lies between 0 and 1, then this particular vector will become very short, but in the same direction only. In the same direction only it will come. Let's say this is your v vector, and I'm just drawing parallel. Okay, so just don't get confused. So if this is your v vector, and if I multiply it with lambda, so what it is going to be? It is going to enhance. The length is going to get enhanced. Okay, so I'm just drawing it with red pen. So this is going to be lambda times v vector if lambda is greater than 1. If lambda lies between 0 and 1, then what would happen? If lambda lies between 0 and 1, so this will get shortened up, but in the same direction. Okay, but in the same direction. So this is the case when lambda lies between 0 and 1. So and similar things you can think for lambda less than -1, the direction would be changed, but one can understand that the scalar multiplication is well defined. Now, if I take any scalar, let's say alpha, and if I take two vectors, that is v1 vector plus v2 vector, it is equal to what? It is equal to alpha times v1 vector plus alpha times v2 vector. This was the second property when it came to the scalar multiplication. The third property was, I think, the associativity. So alpha beta v vector is equal to clearly alpha b v vector. Okay, so basically what does it mean? Let's say if I'm saying that my vector is just for example, let us take our vector to be let us say 1, 1. So I want to write that my vector is I cap plus j cap, simply I cap plus j cap. If I multiply it with 10, or if I multiply it with 2 into 5, or if I multiply 2 into 5 I cap plus 5 j cap, this is one and the same thing. So basically associativity holds. Basically sort of what you can say, I should say associativity, or should I say, so you can take it as an associativity also. So basically whether you write 2 into 5 I cap plus j cap, that is 10, or you write 2 times 5 I cap plus 5 j cap, they are one and the same thing. So this operation is also valid. This operation is valid. Scalar multiplication is well defined. And there is an identity element also. So if I'm talking of r square, so you know that in r square, in the Cartesian plane, there is a vector called as 1, 1. So there is an element 1, 1. Sorry, not element 1, 1. There exists a scalar. There exists a scalar. Exists a scalar 1. So because I'm taking entries from real numbers, so there exists a scalar 1. So if I multiply this scalar with the vector v, I will get back the vector v. So basically there is an existence of identity element here. Okay. And the last thing is distributivity. So if I do this alpha plus beta times v vector, it is equals to alpha v vector plus beta v vector. Understand this v vector I'm taking right now for simplicity from r square. So basically I'm discussing the space r square over r. So basically what I'm discussing this space r square over r. So I'm discussing r square over r. So clearly this r square over r qualifies all the definition required for the vector spaces. So therefore I would say this r square over r forms a linear vector space. This is the first thing that needs to understand. One needs to understand that what is a linear vector space? A linear vector space is one which follows all the properties that I've listed before. Okay. This is the first thing that you should understand. Now what happens is, lately you will come to understand that what is the physical interpretation of this psi. So as such, psi does not have a physical interpretation, but psi mod ka whole square does have. So if I integrate this psi mod ka whole square from -infinite to +infinite, it represents the probability of finding the particle anywhere in the space, and this should be unity, because there should be somewhere that particle should be present. So basically, I'll come to this in the later postulate, but I think from standard from your BSc sections, you know that. So we need to define a space where you can have these kind of operations to be valid, and this space is called as a space of squarely integrable functions. So you need your wave functions such that they are squarely integrable, because if they are not squarely integrable, then you cannot define the probability. So you need a space of square integral function. This is the first prima facie requirement when it comes to defining the wave function. So your wave function psi must be such must be coming from a space of squarely integrable function. This is the first thing. Okay, this is the first thing. And mostly we are going to this is uh, in mathematics we write it in L square. So basically we are going to discuss this only. We are going to discuss this thing in very greater detail. Now let us come to the let us come to the uh, let us come to the Hilbert space. Just giving you an idea. Okay. Another thing that one needs to see is an operation called as inner product space. Now, what do you mean by inner product space? So you can right now consider it analogous to scalar product. If I'm taking R square, so for example, if I have a vector A vector and if I have a vector B vector, then A vector dot B vector should be A1 B1 plus A2 B2. This defines a scalar product of A vector and B vector, and this A vector and B vector are from R square. Okay, and if I want to generalize it in n dimension, let's say this is an element in Rn, that is it. Instead of having instead of having written it as A1 I cap plus A2 j cap, and if I write it as A1 I cap plus A2 j cap plus A3 k cap, if I write it in this fashion. So basically, let's say if it has n tuples, let's say if it has n tuples, and this B vector also has n tuples, then what would be the scalar product? This I would write it as something called as inner product. So A, with the inner product of A vector and B vector would be then A1 B1 plus A2 B2 plus A3 B3 dash 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 A and Dn. Okay, right now I'm taking A and B to be real elements. If I don't take them real elements, and if I just consider the most generalized sort of definition for the inner product, then this would be A1 conjugate, A1 star, that is the transpose conjugate, then A2 B2, A3 B3 dash 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 AN star Bn. Okay, right now just take it as a definition. Right now just take it as a definition. Once we are going to start with linear algebra, we are going to discuss it in more detail. Okay. Now, as I told you, in quantum mechanics, we need that the wave function should be squarely integrable. What does it mean? It means that the integration from minus infinite to plus infinite, psi mod ka whole square should be equal to 1. Or if I just integrate it from some point A to B general, then psi mod ka whole square dx must be a convergent integral. It must be a convergent integral. Okay, the set of all these squarely integral function, the set of all these, this is something that we are going to see in greater detail in linear algebra, but set of all these squarely integral functions form a linear vector space. Okay. And this is you can say this is a kind of Hilbert space that we are talking about when it comes to physics. So this is a kind of Hilbert space we are talking about. One of the kind of, you can say this is one of the kind of Hilbert space. What space that we are talking about. Now, more mathematically, if I want to elaborate, What should I do? Okay. So if more mathematically, if I want to elaborate, I'll elaborate it in this way. Okay. So I've just given you a zeal of it. So first thing is these are the square integral function. Okay, square integral function means scalar product is well defined or inner product is well defined. Scalar product I'm writing in if these are a vector and b vector, then I have defined a scalar product as a1 b1 plus a2 b2 if a and b are both real are elements of the real vector space. So if it is not the case, then in general I would write it as a1 star b1 plus a2 star b2 plus a3 star b3 dash 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 an star bn. This star is transpose conjugate. Okay. So so these squarely integral functions form a linear vector space, and most of the physicists in general associate with this kind of set of squarely integral function as Hilbert space. Okay. Now, more sort of mathematically, how can I define it? Let me just try. Let me just try. A few of the things probably you may not be able to follow, but just let me try. First thing, what is a Hilbert space? Okay, I'm just writing all these things in quite abstract sense. Okay, so these are not very rigorously mathematics, but just what is required for you to understand when it comes to physics. Okay, so first thing is what is a Hilbert space? So Hilbert space is nothing but it is an inner. It is a complete. The first terms that come is complete, and this is again a difficult term. Okay, difficult as in it is a topological term. In mathematics, but let me try my level best. Complete inner product space. So one thing is clear, that the space should be complete. What is complete, that I will come to let you know, and what should we understand as a physicist with respect to completeness. The first thing is what mathematicians associate themselves with completeness. I'm going to give you just an abstract idea. This is a very big topic in itself when it comes to mathematics. What is inner product? I've already stated inner product is this kind of operation. And with respect to space, I mean, I want to suggest this as linear vector space. So the first property the first property that one needs to understand is one thing is when it comes to these, like for example, when it was these vectors now, so we can define this inner product in this fashion. How to define inner product when it comes to squarely integral functions? So I have already stated that we are going to study we are going to study in quantum mechanics the wave function, and these wave functions are nothing but these are the square integral functions. So basically, what do I mean by inner product? So what do I mean by inner product when it comes to the? So basically, inner product I can just simply write as a scalar product. So if I'm doing scalar product of A and B, what do I mean? I mean it is equal to A1 B1 plus A2 B2. Okay, so this is it. But if I don't want in this fashion, but if I'm talking about square integral function, what does inner product there means? So inner product of two functions, let's say in interval a comma b, if I'm speaking, it would be equals to this integration, that is f star g. This is what I mean when I say I'm doing some inner product. And just excuse me if I'm using this kind of notation right now. I'll make you understand what I'm doing it. So basically, this is a cat and bra notation. This I'm going to come to it slightly in a later section, and that would actually conclude the entire discussion of this state vector. Okay, so this is what I mean when I say inner product of two functions. Okay, when I say inner product of two functions. Okay. And one of the very important properties is that if this is one of the very important, you can say, sort of statement, if both f and g are squarely integrable, if both f and g are square integrable, this is without proof I'm writing, if both are square integrable, then their inner product would exist. You can say inner product is sort of would exist, would definitely exist, I would say. Inner product would definitely exist. Okay, this is the first thing. Okay, so now when it comes to Hilbert space, I have written it is a complete inner product space, and in these Hilbert space I am more concerned with the square integrable function. These set of all these square integral functions form a linear vector space. This is something that we are going to derive in later section, because this again would become a very big lecture otherwise. So just I'm giving you a hint. You can just try it at your own convenience. Otherwise, I'll do it for you. The set of all these square integral functions form a vector space. And now, what is Hilbert space? So basically, this is what we associate as physicists. We associate by Hilbert space this kind of space where we have these square integral functions. And you should understand why we are talking and why we are interested in square integral functions. We are interested in square integral functions because, see, in order to define the probability, we need this kind of formula. We need this integration to exist. If this integration does not exist, then how we are going to define the probability of finding a particle in the space from x to x plus dx? This is something that we are going to do in postulate number 3. But right now, I'm assuming that you know quantum mechanics till BSc. Okay. So Hilbert space. So first thing that that Hilbert space, let's say if I'm defining it in this sense, H. So first thing that one needs to understand is that this H should form a vector space. So it should form a vector space. So it should itself form a linear vector space. And what is a linear vector space? That I have already discussed. This itself should form a linear vector space. The second property that instantly follows is that H should have a defined inner product or scalar product. Defined inner product which should be strictly positive. Because probability cannot be, lately you should understand that probability cannot be negative. So this integration cannot be negative. So it should be strictly positive. So in general, what do I mean by inner product or scalar product? As I've already mentioned. So if I'm talking of scalar product of psi with phi, or with basically this particular quantity is a complex number. In general, it is a okay. So if I just what you should say, in general, it is a complex number. So if I just turn this operation to phi and psi, then this phi psi, it would be equals to it is not always in general. This kind of commutative operation is not always true. So basically what we do, we take this kind of thing. So this is one of the property that holds. So that holds. Okay. So what do I mean when I say a scalar product? I've already stated inner product that is defined by this, or you can say this. Okay, or you can say this. And when I say this, what I mean, if I'm saying if I'm saying f, this kind of bracket I'm doing, I'll come on to this later on. This itself means I'm writing integration from a to b f complex. This is complex conjugate and transpose Vx is equals to, if you just take the conjugate of it, if I write just this way, I have to take again a conjugate. So basically, this is equal to this. Okay, so this is equal to this. Okay, so this is first thing that one needs to understand. This is the first thing that one needs to understand. Okay, these are just properties. So first thing is clear that H should have an inner product. Inner product is defined by this, and there's one property that if I'm writing psi comma phi, that this is a scalar product, then this in general is a complex number and it follows this equality. Or in general, when I write it in integration sense, then it follows this equality. Right now, just take it as a concept, as a fact right now. Okay. Now you see, the other thing is, if I consider the scalar product of phi with respect to linear combination of some vectors. So let's say if I'm considering the scalar product of phi with A psi 1 plus B psi 2, it is equal to, I'm just defining this some properties. So how this particular scalar product would behave? It would be like A would come out, right? A times phi into phi comma psi 1 plus B times phi comma psi 2. And instead, if I use this particular thing in the first of the on the first like ordered pair, if I use here this particular A psi 1 plus B psi 2, if I write in the first place in this ordered pair, if I write phi here, it is equal to A star phi 1 plus psi 1 comma phi plus B star psi 2 comma phi. Okay, and now if I again take this complex conjugate for this, I'll get back this. All of these things we are going to discuss in more detail when it comes to linear algebra. Don't worry about it. Just understand that this is some property, that if I'm saying that some system is some particular set or some particular space is forming a Hilbert space, the first thing that one needs to be seen is that whether it forms a linear vector space. Secondly, whether there is some well-defined inner product which is strictly positive. What would be the scalar product of A with itself? What would be the scalar product of A with itself? It is going to be A mod ka whole square. Okay, it is going to be A mod ka whole square. Similarly, if I write it in the integration sense, if I'm doing the inner product of F with respect to F, that is, if I'm dealing with functions, then it is going to be integration from A to B, F mod ka whole square dx. Clearly, F mod ka whole square would be greater than equal to 0. So therefore, this is strictly positive. This is strictly positive, and it is equal to 0 only if F is 0. Only if it is F is 0. Okay. Now another property is that H must be a complete space. H must be a complete space. Now, what do we mean by completeness? In more abstract sense, I'm going to talk. H must be complete. H must be complete. See, if I say that a set is complete, let's say if I'm talking about set of real numbers. If I'm talking of set of real numbers, I say that my set of real numbers is complete. Why do I say? I say it because if I take any sequence of set of real numbers, a sequence of set of real numbers will always converge to a real number. set of sequence of real number will always converge to a real number. Okay, it will always converge to a real number. If this is the case, then we say that the set of real numbers is a complete space. We say that the set of real numbers is a complete space. And this is quite easy to see from something called a sandwich theorem. Okay, so let's say if I know that between any two real numbers there again can be infinitely many real numbers. Okay, so r minus 1 by n से लेकर r plus 1 by n, if I just take all the elements of sequence here, okay, then what would be the limit Rn? So limit Rn would be equals to r. From sandwich theorem, it would be equals to r, because as n tends to infinity, this will go to 0. So this is tending towards r, and as n tends to infinity, this is going towards r. So basically, limit Rn is equal to r. So any sequence, and this r is any arbitrary real number. This r is any arbitrary real number. So if I consider any sequence Rn which belongs to r, and if I take the limit of it, so the limit would converge to another real number. So we say that this real number forms a complete space. In an analogous way, what would I mean about what would I say? What would I mean that H is a complete space? So if I consider any Cauchy sequence, by which I mean any convergence sequence. If I take any convergence sequences in Hilbert space, then this should converge to an element of Hilbert space only. This should converge to an element of Hilbert space only. So basically, if psi n belongs to H, that is, if I take any Cauchy sequence psi n from here Hilbert space H, then this particular sequence should converge to an element of Hilbert space only. Okay. So by this, I would say that my space is complete. Like a set of real numbers form a complete space. They form a complete space. Okay. They form a complete space. Similarly, by completeness, we mean this. However, in basically when we say that a set is complete, okay, a set is complete, or you can say a set of wave function is complete in physics. What do we mean there? Okay, what do we mean there? So let me just focus on that. Okay, let me just focus on that. So here completeness is a topological term, but what do we mean when we say that a set of wave function is when we say that a set of function is complete? What do we mean? What do we understand when we say that a set of function is complete? Okay, by which I mean, so for example, the first thing that one needs to understand here again is what is the concept of orthogonality. What is the concept of orthogonality? So two functions fm and fn are orthonormality, I should say. Orthonormal. So first thing that one needs to understand before understanding that set of functions are complete or not is orthonormality. Fm and Fn are orthonormal to each other. They are orthonormal to each other if they are orthonormal to each other if what? If Fm star Fn dx integration, let's say orthonormal to each other in an interval a comma b is 0 if m is not equal to m, and it is equal to 1 if m is equal to m. Okay, so then these functions are called as orthonormal to each other. Okay, and we say that the set of function is complete. Set of function, let's say f is complete if I can express my function f in linear combination of these orthonormal functions. in a linear combination of these orthonormal functions. Let's say we are talking of infinite dimensions, and I'll come to what is dimensions also later on, but just understand this thing. Okay, so we say that the set of function f is complete if f can be written as linear combination of these orthonormal functions. So this is what we mean by complete. So one can understand till now whatever I have stated is what is Hilbert space and what is the state vector. So the first thing that is quite clear, is that any quantum mechanical system, the state of that particular quantum mechanical system can be specified by a state vector which was given in this fashion. Okay, and that particular state vector resides in the Hilbert space. Okay, so first thing that I emphasized on was Hilbert space, Okay, and in order to make you understand what is Hilbert space, I went through vector space, and these are just very less rigorous kind of approach. Probably it may seem to you very rigorous, but this is very, very less rigorous, whatever I've written. And I have stated all those things that are required, that we required in order to define the linear vector space. And what is Hilbert space? Hilbert space is nothing but it is an inner product space. That is, H should form a linear vector space. H should have a well-defined inner product, which I have defined already, and H must be complete. When I say complete, when I say that set of real numbers is complete, what do I mean? That for every real number, there is just a sequence which converges to that particular real number. If this is the property, then we say that real number system forms a complete space. Similarly, when I say that Hilbert space is complete, so if there is a wave function psi n, or if there is an element psi n which is a Cauchy sequence, which is a convergence sequence in Hilbert space, then psi n, if when it converges, it should converge to an element in H. So this is kind of a completeness we mean completeness in this sense. But what is completeness in sense of function? So if I say that my set of function is complete, then one needs to understand what are orthonormal functions first. So the two functions are said to be orthonormal if integration a to b fm star f dx is equal to 0, if m is not equal to n, and if m is equal to n, then it is equal to 1. If this is the property, then fm and fn are called as orthonormal functions. And if my function can be expressed as the linear combination of these orthonormal functions, then my set of these function f is said to be complete. So this is what we are going to see later on, that the wave function that we say in quantum mechanics is complete in this sense. Now, obviously, the wave function is a part of Hilbert space. So obviously, this is complete in basically because since Hilbert space itself is a complete space, so it is complete in that sense also. And when we say that my wave function is complete, it implies that the wave function can be represented as a linear combination of some orthonormal functions. This is something I'm going to emphasize when I'm going to do, let's say, a particle in a box. Okay, so at that particular time also you're going to understand. Don't worry about it. If you're not able to follow it right now, just write it down somewhere. Now, so first, the concept is very much clear that that the state of the system is specified by a state vector, which was actually sort of defined this way. What is this way? This is called as the Dirac notation. This is representation of my wave function is in Dirac notation. And I hope, because since this particular lecture has become very long, so I'll touch upon this Dirac notation in the next lecture. I will touch upon this Dirac notation in the next lecture. Till then, take care, and I hope to meet you in the next lecture with a discussion, a very slight discussion on Dirac notation and a slight recapitulation of this this concept of linear vector space. Okay, so I hope to meet you tomorrow in the continuation of this series on on postulates of quantum mechanics at first, and then we are going to we are going to take this theory forward. Till then, take care. Bye bye.